Hello, my name is Kyle Schweitzer, and this is my video presentation number 3 for ME304. Okay, so we're given the following problem. For the following beam shown loaded below, find the principal stresses and the maximum shear stress at point A, and we're going to use the coordinate system below. So here's our beam. I've already drawn it just to save some time. I've also drawn in the dimensions. So we got 32 millimeters high here, 60 millimeters wide, 30 millimeters from the center to A, obviously half the distance. And this is our point of interest, point A, which is located 24 millimeters away from the fixed end. And then we have our loads. Our first load, 750 newtons, is 180 meters away from the point of interest. So 180 millimeters here. And then the rest of the loads are located in the center of the face, the end face, which is another 40 millimeters away from the end, to give you a grand total of 220 millimeters from A. And then we have 16 millimeters, which is obviously half 32, to the center. And there's where our 500 Newton and 10 kilonewton force are being applied. All right, so to solve for the principal stresses and maximum shear stress, we have to go through a certain process to isolate the point of interest and then solve for the principal stresses after we have solved for a number of reaction forces, and you'll see the reaction forces will show us the stresses inside point A. And so for the first step, we're going to need to create a transverse cut at our point of interest. And we're doing this to isolate the face that A is located on. And then we're going to solve for the reaction forces going through the origin of the center of the face where we make the transverse cut. So following this coordinate system, so Z is coming out of the side, going this way. Y is coming up and out of this face, up out of the top face. And X is our, it will be our, consider our longitudinal axis, and it is coming through the center of the axis, center of this beam, just through this face. Same direction the 10 kilonewton force is coming out. Okay, so we're going to make our transverse cut at our point of interest, and I have already done that just for the sake of time. And so here we have our transverse cut made here through A and down. So we have A now on the end of the face. It is the end point, and through the axis we have our reaction forces, our Y, our Z, our X, MX, MY, and MZ. And this is just, we're going to solve for the location of the forces, and then the reactionary forces are going to be creating equilibrium based on the what the forces are doing to this beam. And so our Y would be a positive Y direction. Our Z would be a positive Z direction, so it's coming out this way. And our X would be a positive going out through the center of the beam. And for moment, we have each moment going around the reactionary axes, or the axis that we're starting with, and each one is going in a counterclockwise direction, which is denoting a positive moment. And if you were to look at these axes individually, you can see that I've attempted to draw each moment going in a counterclockwise direction. Okay, so now what we need to do is we need to create a chart for the location and the force and the moment. And this will allow us to solve for our reactionary forces, our Rx, Rz, and Ry. And so we do that by just creating a simple table, which I've done here, just to save some time. But it is done by solving for the vectors. The vectors are F and M, R being the location or the distance from the origin in Y or I or X, Y, and Z, and then our force being the direction of the force and whether or not it's positive or negative, and that is also in the X, Y, and Z. And then moment we can simply find by cross producting or taking the cross product of R cross F, and we will solve for our moment based on the forces. So we're going to go ahead and start with the 750 Newton load. Make sure you can see this. Okay. So we're going to start with the 750 Newton load, which is located from the origin. It is a distance of 180, as seen up here. So from A to this point, we have a distance of X positively at 180 millimeters. Now I'm going to write this down as 0.18 because I'm converting to meters, and this is just simply because if we were to keep it in millimeters, we would have a much larger number coming out for the moment, and it's just a little bit easier to work with these smaller numbers, as you'll see. But that is what I'm doing. That is why I'm putting 0.18, because I'm changing it to meters. So the distance in the Y direction, which is going up and down, will be the distance from the origin to this point, which is the height from the origin to the point A. And we solved here from the center, which would be the origin. If you follow this back, it would be the origin up to the top, which is where the 750 Newton force is. It would be 16 millimeters. So we put 0.016, and it goes nowhere in the Z direction. Oh, geez. It goes nowhere in the Z direction. So that is just a 0. Okay, so now that we have our R vector, our direction vector, we can now solve for the force vector. And this is simply done by looking at the direction of the actual force. So for the 750 Newton case, the X direction, it's not pushing or pulling in the X direction. So we have a 0 there, and it is in the Y direction. It is following the Y axis, and it is going down compared to the positive, which is up. So we have negative 750, and that is newtons. And then again, it's not pulling or pushing in the Z axis, so we have a 0 here. Okay, so now we can just take the cross product of these two vectors, 0.18, 0.016, 0, and then 0, negative 750, and 0, and we would get the moment vector. And that would be 0, 0, negative 135. Okay, so now that we have that, we can move on to our next load, and we're going to solve for the 500 Newton load, force, I meant. So again, we go through the position, which is from the origin to this dot, which is where the force is being applied. We have just an X value, and that X value would be from point A. So from point A to this C, which we can just put here to solve for the X, and it is 180 plus another 40, which is 220 millimeters, or 0.22 meters. And again, it's 0 in both the Y and Z direction. It is not going up or down because it is on that reaction. It is on that reaction force axis. And so the force, again, it is pushing only in the Z direction, and it is a positive because the positive is denoted as going out into the left of the page, so out to the left, and it's also pointing out to the left. So we have a positive 500, and that is in the z direction. So we have 0, 0, 500. Okay. Let me zoom in a little bit just so you can see for sure. All right. So now we just take the cross product of these two vectors again, and we get 0, negative 110, 0. Okay. So now we have our finally 10 kilonewtons, which is 10,000 newtons. And again, we do the same thing. It ends up being at the same location as the 500 Newton force. So the location vector, or the direction vector, is the same as the 500 Newton. And the only thing that changes is the force vector. And the force vector, in this case, it is pulling in the positive x direction. So x will be a positive 10,000. And it is not pulling or pushing in the y direction. It is not pulling or pushing in the z direction. So 0 and 0. And taking the cross product again, we get 0, 0, and 0. Okay. So now we have our forces, and we have our moments. And our forces is directly associated with the reactionary forces, and the moment is directly associated with the moments. And the way we solve for Rx, Ry, Rz, Mx, My, Mz is just simply through equilibrium. So this is showing that there's a 10,000 kilonewton, or 10,000 Newton, force in the x direction. So there's going to be a negative 10,000 reactionary force that creates equilibrium. And then same thing for y. There is a negative 750 Newton force in the y direction. So we have a positive 750 Newton reactionary force in the y direction. Same with the k, we get negative 500. Same thing applies there. Moment of x, it's the same thing. It's 0 because there's no reactionary moment in the, or there's no moment in the x. You'll see that kind of makes sense after I point that out. But we're just going to finish this real quick. Moment at y is 110 because the reaction will be positive 110 to denote the negative 110. And then for y, or z, sorry, it would be 135. Okay, so now we kind of want to see, does this make sense? And it's pretty easy to see in the reactionary forces that if you have a positive x, you're going to have a negative reaction. If you have a positive z, which is the 500, you're going to have a negative reaction. Same thing applies for both these. But then if you have a negative y reaction, negative y force, you're going to have a positive y reaction. And then this takes a little bit more explaining, but the moment in the x, these forces, if you look at each one, none of them are going to create a rotation about the x axis. And you can just tell because the 750 Newton force is going to create a, if you put your pencil here, and this is the beam, if you push here, it's going to rotate on the axis of z because that's just how it will work. If you push down on here, it's going to rotate about the z axis. So we know that z is going to have some sort of moment, and the 10 kilonewton force is not creating a moment at all because it is along the longitudinal axis, and it is not creating any torque or torsion or anything like that. No moment is applied. And the 500 Newton force, if you have, again, you have the beam here, and you're pushing here, you're rotating about the y-axis, the axis that comes through the top. If you put your beam here, put a force here, you're going to be rotating about that y-axis. Okay, so we have a y moment, which all makes sense. Okay, so now we have to identify our longitudinal axis. And I've kind of said that before, but the longitudinal axis in this case is the x-axis. It is the axis that goes through the center of each face, and that would be the x-axis. So we're going to go ahead and label this the longitudinal. And that is going to help us later on in our when we're going to be solving for the individual stress due to each load type. We're going to use that as a reference to what each reaction force is going to create on the beam. So we're going to go ahead and start that. And it is simple to start with the axial force, which will be Rx, because on the longitudinal axis, the force on that axis is the axial force. And so I'm going to go ahead and put this over the side, but we're going to come back to that later just to see the values. But Rx will be axial. And we're going to have to draw a cut for this. So for the axial stress, we're going to cut the block same way we cut through this transverse cut. We're going to cut it on the right side of it so that we just see a little segment of A. And as you can see from here, we have the values for the RY, RX, and all the M's, all the moments, so that we're going to isolate our X, which is a tensile, which we'll see. Yes, sir. I'll show you. Okay, so we're going to cut it the same way we did, and we're looking at the left side. So we're looking down the z-axis, and you can either choose, you could choose the y-axis or the z-axis, as long as you're looking at it from the one of the other axes, not the longitudinal axis, one of the lateral axes. So I'm going to pick the z-axis. So if we're looking at it from that, we'll have x going out this way and y going up, and we'll have A in our top corner. So like I said, we're looking at it from the z-axis, so we have x going out to the right and y going up, as denoted here. Okay, and then for our Rx value, we have a positive, for our Rx value, we have a negative Rx. So to draw this, we have a negative reactionary force, which negative will be going opposite the x-axis, negative 10,000 newtons. Okay, so now to solve for the stresses, because we have this, the location of A is up here, and because this is a negative force, you could see that this block is being stretched. It is being pulled instead of compressed. It is being pulled by this negative 10,000 Newton force. Well, it's not negative here, but it is denoted that it's negative because X is going to the right and it is going to the left. So we have a tensile stretching force. And for that, it is a positive value. So our stress is equal to P over A. And we simply just plug in 10,000 newtons. And then for our area, we have the area of our cut, which is 60 millimeters by 32 millimeters. And that is denoted in the first picture. It is 60 by 32. So the area of that cross section, that cut, will be 0.06 by 0.032, and that will be our area. And then it just solves out to stress in the X is equal to 52 million, or 5,208,333 pascals, or 5.2 megapascals. Okay, so I'm going to underline this because this is important. That is our stress due to our axial force. And sorry about the barking, but okay, she stopped. Sorry. Okay, so we have our stress in the x direction, and we're going to go ahead and draw. Our next step is to draw our stress blocks for the axial forces, and I'm going to put it on a separate piece of paper so that when we combine them together, it is easier to see where they are all coming from. So we have our stress block number 1, and that is denoted in the, I'm just going to put 1 here so you can follow along, but we have our stress block 1, and the stress blocks are drawn in the same way each time. It is just 3 separate blocks with 3 separate orientations to denote where your stresses are. And it's pretty simple to draw. So for the first one, you have x to the left, y down, x. In the second one, you have x to the left, z up. And then for the third one, you have z up, y to the left, or right. And you're going to see that they're the same thing for each one. And because we have the stress in the x direction, it is a positive 5.2 megapascals because it is stretching. It is a tensile force. We're going to have a positive x stress. What is a positive and a positive? And I'm going to put this in the middle just to save a little bit of time. But this is 5.2 on each side, each block. Okay. So that is our first stress blocks. And now we can solve for our second reactionary force. And with that being the 750 in the RY. And here we have RY going up. And because that is a lateral direction, lateral axis, we can see that the lateral direction on the face of the cut is going to be a transverse shear on the location A. So for RY, a lateral reactionary force, we have transverse shear. And you can kind of see that the RY force is going to be shearing, the block. So it's going to be going straight back up towards, up and out of the paper, up and out of the top face, and is going to be shearing the beam. So we're going to solve for the transverse shear at that location, the point of interest A. And this is done again by doing the same cut so that we can isolate A. So we don't have to look at the entire block. And it is the same thing. A is going to be on top, Y is going to be up, and X is going to be here. And so for transverse shear, what you're going to do is you're going to look at the opposite lateral axis. So if you have an RY, which is a lateral axis, then you're going to look at the other lateral axis, which can't be X because that is the longitudinal axis. You're going to be looking at the Z axis. So we have RY would be a positive 750 as denoted in our reactionary forces. So we have an RY going up, and that is 750 newtons. Okay, so for transverse shear, we're going to look at the neutral axis, and transverse shear is equal to VQ over IT, where V is the force, the shearing force. Q is going to be a value that we solve through, here, I'm just going to put it. Q is going to be Y hat prime A prime, and sorry. And we're going to see that y hat prime is going to be a 0th value, because y hat prime is going to be the distance from the neutral axis to the, a is going to be 0, because a is the outermost area. So from the point of interest, the a value in Q is going to be 0, because you'll see later on, for when we're solving for RZ, you're going to see where a is coming in. But because a prime is 0 in this problem, we know that transverse shear is going to be 0. Because Q is 0, the whole thing goes to 0. Okay, so now that we have that, we can move on to our next reactionary force, and the next reactionary force is RZ. And again, because we have transverse shear 0, our stress block for number 2 is going to be nothing. There's no stress due to that reactionary force. Okay, so now we're going to solve for RZ. And again, that is another transverse shear because it is a lateral axis. And again, you're going to look at the opposite lateral axis to look at the transverse shear. So the opposite in this case would be Y. So we're going to cut the beam same way we have been, except this time we're going to have a different orientation. We're going to have X going out to the right. X going out. And in this case, we're going to have Z going down. And this is, so we're essentially looking at the top of the, we're looking down the y-axis, we're looking at the top of the beam. So A is going to be in the middle, and Z is going to be coming down, and X is going to be right. So that you can see that here. If we're looking at the top, X is right, Z is down. So X is right, Z is down, and A will be in the middle. A is there. Okay. And then for our RZ, we have a negative 500, and since Z is positive going down, we're going to have a negative, which is going up, 500 newtons. Okay. So transverse shear, like I said, is VQ over IT. And this time I will explain a little bit more about the equation. V will be the shear. Q is going to be the first moment of outward area. So again, Y bar prime, A prime. And then I is going to be the area moment of inertia, and T is going to be the thickness at the point of intercept. Okay. So we're going to solve for the I and Q, and we do this by looking at the end view, which is going to be looking at it from the face of the cut. And here's how we denote that. The end view would look like this. So A is in the middle. And here we have the neutral axis going through. And because A is now in the middle, and if you were to flip this, so this is how you know that is wrong. If you were to flip this going this way and have the long axis be on the top and the bottom, the long dimension, I guess, you would see that A is on the top, and again, A would be 0. So transverse shear is 0, but in this case, we're drawing it so that the longer dimensions are on the side, so that A is in the middle. And we have our outward area, which is from the point of interest outwards, and it is from the neutral axis in this case. And then we have Y bar prime, which is the distance from the neutral axis to the center of that area. So halfway up is y bar prime. Okay, so we need dimensions on this guy, and this is easily done by looking at the end view. Sorry, one second. We should actually solve for I first, which is using the base and the height. It is 1/12 base times height. And this again is the area moment of inertia. And so we're going to solve for this, and we get negative 500 newtons, which is, oh, sorry. Completely lost track. Sorry. Okay, it's 1/12 times the base, which is 0.032. That is this value here, or the base down here, times the height, which is going to be the longer dimension of the face, which is 60.06 cubed. Okay, and that comes out to be 5.76 times 10 to the negative 7th meters to the 4th. Okay, and then we're going to solve for Q, Q being the outward area, y bar prime, a prime. And again, y bar prime would be, this is 60, so half of it is 30, and then to the half of the half is 15. So we have 0.015 times. And then the area, outward area, again, we have 32 by 30. So we have 0.03 times 0.032. And so Q is going to come out to be 1.44 times 10 to the negative 5th meters cubed. Okay, so now we have I and we have Q, and then thickness is just going to be the thickness here. So again, it's the dimension 0.32 or 0.032, which is 32 millimeters. And so we could just plug everything in. So 500 times 1.44 times 10 to the negative 5th, and that's meters cubed. And then we have I, which is 5.76 times 10 to the negative 7th, and that is meters fourth. And then we have T, which is the thickness here at point A, which is 0.032, and that's meters. And so then transverse shear comes out to be negative 390,625 pascals. So we can convert that to negative 0.39 megapascals. And so we underline that. And then we draw our stress block 3. And for our stress block 3, we are showing that we're drawing the same stress blocks again. Y down, X here, Z up, X left, Y right, Z here. Okay, and then because we're solving on the XZ plane, we're going to have that transverse shear on the XZ stress block, and that's going to look, and because it's a negative, if you wanted positive slope, it would be going this direction, and the arrows would be pointing towards the locations that the pencil is going through the block. But because we have a negative, it is going like this, so we draw our arrows pointing to the location that the pencil was going through to denote a negative shear, and we have 0.39 megapascals. Okay. So now that we have solved for all the reactionary forces, we can move on to the moments. And we only have 2 moments. And so we can start with a new piece of paper for the moments. I'll put this over here. So for the first one, we have moment about Y. And moment about Y, in this case, would be a bending moment because it is along the, if you have a moment about the lateral axis is going to create bending on the beam. So we have My is bending. If we were to have an Mx, which we do not in this problem, we would have a moment about the axial or the longitudinal axis, and that would be a torsion, which sorry, take a drink. We do not have that in this case. So looking at a bending, we're going to do the same type of cut again, and this time for My, you look at the axis. That the moment is acting upon. So we're looking down again on the y-axis, where A is going to be in the middle, X is going to be coming out to the right, and Z is going to come down. Okay, and then moment, if this was the y-axis, if we have a moment about that axis, and moment Y is again positive 110, it would be a counterclockwise rotation around that axis. So the y-axis is coming out of the paper, and so the counter rotation around that axis is going this direction, and it is going 110 Newton meters. Okay, so this creates bending, and because we are solving for stress, we're using the bending equation for stress, which is equal to MYI over I. And in this case, the Y is, I was kind of jumping ahead on my last one, but Y is the distance from the neutral axis to the point of interest. And so in this case, Y is equal to 0 because the point of interest is on the neutral axis. And you'll see for the MZ, but that is because from this point, which is the farthest away from the neutral axis, you're going to have it's going to be pulling it. It's going to be a tensile force on the top, and it's going to be compressing the bottom part of this. And you can kind of make sense of this because as you're bending this, you're going to be pulling the top and pushing the bottom. And so in the very dead center of this beam is where it changes from tensile to compression. And so as you go through the beam, it is creating a less and less tensile until it reaches 0, and then it's creating compression, which is a negative. And so again, stress in the X direction here is 0 because Y is 0. Okay, so then we can move on, and I could use my stress blocks, and this would be stress block 4. And I'm not going to write it down just for time, but stress block 4 is going to be nothing, just like stress block 2. Okay, so then we can move on to MZ, which is again bending because it is a moment about a lateral axis. And so we can use the same type of cut. We're looking down the Z axis this time. So we'll have X and Y, X going this way, Y going up. And so again, we're looking at the side of it, the side angle. So A is going to be on the top left. The neutral axis is going to be going to the middle. And we're going to have 135, which is a positive. And again, if we're looking at it from the side, the Z-axis is coming out of the paper. We're going to have a counterclockwise rotation, which again looks exactly like the top one because it is a positive moment, and it kind of got in the way. But we're going to have a counterclockwise rotation at 135 Newton meters. And this one is pretty simple. We're going to do the same equation as above, My over I, where I is equal to 112.06 in this case is the base, and 0.032 is the height. And I'm just going to plug this in because I do not know that value. So 135 Newton meters for the moment. Y is the distance, and so the distance in this case from the top to the bottom, as denoted here, the middle to the top, is 16 millimeters. So we're going to have 0.016, and then we're going to have I, which I plugged in. I'm just going to plug in like this. And then we're going to solve out, and we get stress in the X, I'm going to put down here, is equal to 13.2 megapascals, or 13,183,593 pascals. And to solve for I, sorry, I should probably put this, but we're looking at it kind of like this, where this is 32 millimeters and this is 16 millimeters. And that is where we get the base and the height, and that is the base and the height cubed. That's solving for I. Okay, so now we have this, we're stressing the X. I'm going to bring back this, our stress blocks, and so we have our stress blocks in this case. Is stress blocks 5, which is our 5th reactionary force, and we can see that is the same and the same stress blocks. And again, we have a positive X stress, and it is 13.2 megapascals. Okay, so now we have each reactionary force, and this is stress block. We have each, We have each reactionary force's stress box. And so now what we can do is we can combine these stress blocks to solve for the total stress due to the forces in the beam shown below. And we can use the max stressed block to solve for the principal stresses. And we could do that by using Mohr circle, or we can just simply use the equations that come with Mohr circle, and those are the principal stress equations, and I will be using those. But first, we're going to have to combine these. So I'm going to draw the combined XY, Z, X, Y, Z. Okay. So we have a positive 13.2 here and a positive 5.2. So we're going to have a positive 18.4. megapascals. And then we just have one shear, and it's in negative direction. So we can just draw that in. That's the only shear we have. And again, it is in the same direction as we have here. So 0.39 megapascals. Okay, so now to solve for this, we're going to use the principal stress equations, and this is denoted by this equation, which is sigma 1 sigma 2 is equal to sigma x plus sigma z over 2. And you'll see why I'm choosing x and z, because in the equation, you can kind of see which is going to be a max and which stress block you're going to choose, because you're going to have to choose the one that gives you the max value. And so that's the equation. And so if we picked xy, we would have only sigma x, and we would not have shear xz, or we would not have shear xy. So this would be 0, and we would be using 18.4 as the sigma x. Or we can add in this 0.39, and we would have a extra value here, which would be bigger than this guy. And of course, zy doesn't have anything, so we don't even need to regard that one. So we can use, that's why I'm picking the xz, because it's going to give us the max value. So we're going to put 18.4 plus 0 over 2 plus or minus, and this is sigma x coming from the 18.4. Sigma z, we have nothing in the z, and divide by 2 plus or minus the square root, and sigma x is again 18.4 minus 0 divided by 2 squared plus, and then we have 0.39, and I'm not going to put negative because it gets squared anyways, but we would technically put negative there, but I'm not going to put that. Okay, so then we have sigma 1 is equal to the positive version of this, which is 9.2 plus 9.21. And it kind of doesn't surprise you that when you take this value here, it's going to be very similar to this value, because this adding on this tiny value is not going to give you that much more. It's actually 0.01 amount of difference, but nonetheless, it is a difference. So we get sigma 1 and sigma 2 is equals negative 0.01 for sigma 2 and 18.41, and this is in megapascals. And then for our shear max, this is simply just, here, I should write max. For our shear max, it is simply just the value that this denotes. So it's going to be equal to 9.21 megapascals. And there you have it. You have our principal stresses and our max shear using the coordinate system below. And this is my red ID. Thank you for watching.